Okay, so this is the class BIOL476. It's spring semester 2025. And today we will talk about hypothesis testing. So this is a very usual and useful approach we have to systematically draw conclusions about a population based on a sample. So the example that I will use today in order to demonstrate how we perform hypothesis testing is the following. So there is a student with a mark of 8.54 out of 10 who is claiming that he is an excellent student and therefore he is asking for a recommendation letter. So this is something given, and something else that is given is that I know the theoretical, I underline this word, the theoretical probability distribution of the average marks of all students. Average here. Okay, and let's suppose that this is this theoretical distribution. It has some mean of 7.82 and some standard deviation. So these are numbers that they're just random numbers here. And based on this number here, and on this theoretical distribution, I have to decide whether the student is a kind of a special student, for example, if he's really an excellent student. So in this case, I'm thinking as following. My observation, let's call it x. Let's have this random variable x that describes the mean mark, the average mark of a student. In this case, my value of x is 8.54. And also I have a theoretical distribution, this one, with 7.82 and sigma equals 1. Let's suppose that this is a Gaussian distribution. So let's say that this follows a normal distribution with these parameters. And this distribution now, this is crucial, represents the average marks of all students. So in this case, this distribution represents, let's put it in quote marks, nothing special. It's actually the distribution of average marks of what I would expect to see if I would pick randomly a student from a department. So in other words, if I randomly get a student, I might observe, let's say, a value of 7.5, a value of 8, a value of 9.1, and so on and so forth. So that the marks, the average marks of not so special student, right, like a random student from this population, would be something like that. And thus I have to decide whether this 8.54 is something special. In other words, if I can make the claim that this average mark comes from this distribution, or if it comes from another distribution, probably with higher mu. So I'm working as follows. I form the so-called null hypothesis, thinking that, okay, let's suppose that x is indeed a value from this distribution. And let's call this distribution P. Now this could be as follows. So this is the mu here, 7.82, sigma equals 1, and my value now is somewhere here. This is the 8.54. Okay, I have supposed that this x, this one, is actually a value from this distribution. And now I go back here in the beginning and I remind myself what this student is asking for. He's asking for a recommendation letter claiming that he's an excellent student. So he's claiming actually that this 8.54 is a very high value. So I have the claim here, or the alternative hypothesis, that, you know what, this 8.54, so the 6 that I have, is higher than what you would expect from P. Which means that this P cannot give such high values so easily, or higher values than this. So this means that P cannot, I put it in quote marks, easily give values as high as x or higher. Now I need this or higher here because since the student claimed that this is an excellent mark, I have to compute how easily I can get such high marks or higher from the general population, from P. So then what I do, so now I have formed the null hypothesis, which is actually this distribution here, and I suppose that x is coming from this distribution, and I have formed the so-called alternative hypothesis, which says that this 8.54 is actually higher than would be expected from this distribution. And having in mind this higher, then I go to this distribution and I compute this area here, which actually represents the following: the probability to get a value equal or greater than 8.54, given that this P is true, given that the student is actually a sample from this distribution. Okay, now let's suppose that this value, this area here, has a value of, let's call it small p. So this area here is so big actually. So the probability, in other words, to observe that that a mark is greater than 8.54, given that this mark is coming from this p distribution, is 0.001. In other words, the probability to observe such a high value, 8.54 or higher, this is all this area here, is just 0.001. Then I can claim that I reject the H0 hypothesis, which states that my student X, or the average mark of my student, is a value from P. I reject this hypothesis, the H0, because the probability to observe such a value or greater given this distribution is really small. In other words, I could say that I don't believe that I get the risk actually to claim that this value is not coming from this distribution, because the probability to observe this value or something higher from this distribution is really small. Let's see two other examples. Again, let's say that we have this distribution here. So this is 7.82. Now I have a mark of 6 somewhere here. So a student is coming with a 6 out of 10. And now someone claims that this student is really bad. It's actually worse than I would expect from the theoretical distribution, based on the theoretical distribution of all marks. So the claim here is that 6 is really bad, meaning actually that this 6 is really low. Okay, according to what I said previously, what I will calculate now is the probability to observe an X here which is smaller or equal than 6. Why? Because the initial claim was that this 6 is really small, really a low value. So I would like to know what is the probability to observe such an X or even lower. How easily such a distribution gives really low marks, marks that are 6 or lower, gives marks that are lower than my observation. Let's say that this area now here is 0.2, which means that the probability to get an X smaller or equal than 6 is 0.2. And perhaps with this value I can claim that, okay, it's not so rare to observe a mark 6 or lower than this. Which means that actually this 6 is not so bad. Let's see another example. So this was example 2, then example 3. Again, we have the same thing. The distribution of all average marks is here. A student is coming with a 7 and says, okay, you know, I got a recommendation letter because I'm a really good student. So x1, the h1 now is that x, that the student is excellent. And his mark is 7. And h0 is that actually the student is that the student is really a student that I would expect from this distribution. That the mark is something that I would expect from this P. Since the student claims that he's an excellent student, then I would like to see how easily I can get a mark 7 or greater based on this distribution. And this area here now, 7 or greater, it's all this area. And this area, let's say that the probability of this area is 0.6. So the probability to get an x greater than or equal to 7, 0.6, which means that it's pretty easy to get a mark 7 or greater, which means that the student is not something extraordinary based on this distribution. So these are 3 examples that will help us to understand the hypothesis testing. So to wrap up here, when I wanted to perform a hypothesis testing, I need some things to have in my hand. The first is to have an observation. This can be, for example, average marks of a student. It can be the height of a student, the height of a person. If the example is, let's say, on population genetics, it can be the value of a statistic like the G+D, or the haplotype heterozygosity called DVH, and so on and so forth. It can be how big the wings of some birds are, size of so some observation. And this observation here, the important is that it's a single number. For example, here, the average marks of a student, my actual observation could be that I have all classes of the student. I have mark 1, mark 2, mark 3, all the marks of all classes of the student. But then what I do is that I calculate an average value, let's call it like that. Here I have a single value, here I have a single value, here I have a single value. So my observation usually should be summarized into a single value. Another example that we will see during the semester is that I have calculated the expression values of a gene, let's say gene 1, and I have the expression values of this gene for some healthy individuals. Let's say these values 7, 8.2, 9.1, and so on, and for some disease individuals 3, 3.2, and so on. These are the values of the expression level of this G1, and then I calculate the average value of these numbers, the average value of these numbers. I calculate the standard deviation of these numbers, the standard deviation of these numbers, and I get also how many values I have in this group. Let's call it N1. How many values I have on this group? Let's call it N2. Here is sigma 2. And then based on these numbers, I can calculate a single value called T, which is mu1 minus mu2 divided by so this value is again a single value, even though initially I had several values here. Several values from the healthy group, several values from the disease group. This is a single value, and this is my observation. The second thing that I need, besides my observation, is a theoretical distribution of my observation, or of the statistic that I have. Let's call it X. So let's say here that this observation is observation X. Is described by a random variable called X. The theoretical distribution of this random variable when the null hypothesis is true. So this means the following: in the case of the student, the null is described by the average marks of all students, in the meaning that my student that came to me is nothing special, it's just a student from all students, does not belong to, let's say, an elite group or to the best group, it's just a random guy from these individuals. So I need the theoretical distribution of this 6 when the null is true. Another example is the theoretical distribution of this T here when actually there is no difference between a group and another group. The theoretical distribution of this T is known. In the case of T, the theoretical distribution of this T is known and described by the T distribution. With a parameter the degrees of freedom, but this is not important. So if I would suppose here that this group and this group is the same, they are coming from the same population, then this T is distributed based on a distribution that is known mathematically, and let's say that it's looking like that. Doesn't really matter. So again, to wrap up, I need an observation. I need a theoretical distribution of this observation when the null is true. The third thing is that I need the alternative hypothesis, H1. An example here is that the student claims that he's an excellent student, which means that from this theoretical distribution, I want to find values that are higher or equal to my observation. If someone claims that the student is really bad, which means that he has a lower mark than expected, I would like to calculate the probability to have the observation x or lower values. The observation could be here also, or lower values, then this could be all this thing. And the special case is when the claim is that the observation is something different than is described by the theoretical distribution. Let's say that the observation is here. If I will not claim now that this x is higher than expected or lower than expected, but I just claim that's different, it means that I would like to calculate the probability to have a value greater or equal, let's say that this is 0 here, to x, or smaller or equal to the minus 6. Because in both cases, if I would get a value here or a value here, this value would be more extreme, more different than my observation. So this H1, based on this H1 and the null and this distribution here and this distribution here, I can calculate the p-value. I can calculate this area, let's say, which has a special name. It's called the p-value. So 4 is calculate the p-value. And now number 5, if p-value is really small, then reject the null hypothesis. Meaning that make the claim that this this x value is not coming from this distribution, because this distribution cannot give such an x or more extreme values so easily. So all these steps are behind the so-called hypothesis testing, and usually the result, the final result, is exactly this p-value, which is exactly the probability to observe some x the same or more extreme than the observed value. This word, the same or more extreme, this extreme is defined actually by the H1. Here the student claims that it's excellent. The same or more extreme means this value or higher. If the student would claim that it's bad, then more extreme would mean this value or even or lower, which is all this area here. If someone would claim that the student is different, then this would mean that it can be either good or bad, so I would go to this area and then to the negative value here and this area also. So these are the steps of hypothesis testing, and whenever you read in a paper that we performed a test and we found that p-value is, let's say, 0.02, and therefore we reject the null hypothesis, then all the steps have contributed to get this result. So usually when we say that we performed the test and we found some p-value, we should say what is the null hypothesis, what is the alternative hypothesis, what is the value that we measure, what is the random variable describing the measurement, the 6 here, how this 6 is distributed when the h0 is true. This symbolized with this way, and actually is, let's say, this distribution of the marks of all students, this distribution of the statistic here, and so on. And then what is the p-value? So this is about the hypothesis. Testing is a really key thing when we have to judge some hypothesis based on some sample that we have. That's all.